Welcome to this Program 2 seminar turned IEU seminar. They were very happy to have Fernando giving us another presentation about his work. This one will be on empirically assessing the plausibility of no-selection bias. Fernando, over to you.
Thanks, Apostolos. Thanks, everyone, for being here, for people joining online. It's always a pleasure to, be here sharing some of the work that I'm doing in collaboration with IEU people to the broader group. Sorry for those who have to see me for the second time over the last 2 weeks, but that's how it goes, when I'm around there. For some reason, I always give a lot of presentations. And this is the summary of what I want to talk about today. It's going to be a very, in terms of number of slides, at least a very short presentation, but there's a lot of stuff that we need to discuss and discuss it carefully. And before I start talking about the more sort of focused things I want to discuss today, the context here is you're doing an epidemiological study and you have missing data. And that happens, and that can be a problem. And so we want to have principled ways to deal with that. And, there's many sort of missing data adjustment kind of techniques like weighting, imputation, whatever. And they all require assumptions, as anything in life. We always need assumptions. And what I want to talk about today is a strategy that we can use to give us more or less confidence that the assumptions we need for dealing with missing data are satisfied or not in a particular situation. So for that, to start, talking about this with precise enough language, I need to introduce some notation, but it's not difficult notation. So throughout the presentation, the letter D is going to denote the variables of substantive interest. What I mean by that? So you have a research question, and to address that research question empirically, you have to measure some variable. So, for example, let's say your research question is whether some exposure causes some outcome. That's your research question, right? So you're going to have to measure your exposure in your outcome, and they are going to be part of D. And you're doing this in an observational study, so you're worrying about confounding. So you also need to measure some covariates to try to deal with confounding adjustment, for example. So those covariates that you selected for a confounding adjustment are also going to be part of D in this example. It doesn't have to be, a causal question like this. I'm just giving an example of what D would be. So D would be the set of all variables that you would care to analyze if you didn't have missing data. So ideally, you would have complete data for D. And if you're in that case, you can just, you don't need to pay attention to what I'm going to talk about next. But it's often the case that we have missing data in one or more elements of D, in one or more of the variables of substantive interest. And in this presentation, I'm considering a slightly sort of simplified scenario where I'm working with this binary indicator S. S equals 1 indicates having complete data for all variables in D. So that means that S equals 1 essentially denotes the subset that would be included in a complete case analysis, and S equals 0, otherwise. And I'm going to be referring to S sometimes as S, sometimes as selection, with analogous names. And as I said, out of your set D, you could have one or more variables with missing data. And M denotes the subset of D that has missing data. And, I'm going to be referring to M as the incomplete variables or M or something like that. And you're also going to have yet another set of covariates that I'm calling C for complete variables. That is, variables that I have data for both S equals 1 and S equals 0. I can have one or more elements of D in C. That is, sum of my variables of substantive interest could be complete, right? And in this presentation, I'm not going to discuss how to go about selecting C. My starting point is, you already selected the set of complete variables you want to use to try to do selection bias using whatever criteria you want to use. I'm not concerned about that in the presentation. And for, any method to work, including the procedure we're going to be describing today, we're going to need some assumptions. So fingers crossed. The first one is that the data, and by data I mean the set S and D and C, is assumed to be generated by some DAG. I'm not saying you need to know the DAG. I'm saying I'm assuming that there is a DAG that generated the data. Because I'm going to be, the proofs for this procedure are going to rely on, arrows and stuff. So I need to assume that that makes sense. The second assumption is faithfulness. And faithfulness essentially says that this separation, like, when there are no open paths between two variables in a graph, that is equivalent to statistical independence. That's not always true, so I need to assume it is true because I'm going to use that at some point. And the third assumption I need is that S is what I call a sink, and by sink I mean there is no error coming out of S. That's plausible in some situations, not plausible in other situations. In observational studies, is mostly plausible. And what is the goal? Well, what we would hope is that the joint distribution of our set of variables of substantive interest D is independent on selection, conditional on the complete variables we selected to try to do with selection bias. If that's true, then I can recover the joint distribution of D in the full population using weighting. You can also do imputation if you want to. I'm just thinking about weighting here. I find imputation too complicated. And if D has some complete variables, then we can just express that independence condition only with respect to the incomplete variables, because that's really what that's really the assumption you need. And of course, because M itself is incomplete, I cannot directly test whether this independence assumption holds. You see the problem? Okay. And what I'm going to try to do throughout the rest of the presentation is to present a procedure that, given assumptions A1, A2, and A3 that I presented in the previous slide, is going to be sufficient for us to assess this indirectly. That's the goal. So this is now going to the meat of the presentation. And I'm only going to present non-parametric results for a very simple reason. That's how far I got. Well, read other than that. So what I'm gonna have show you is a set of 5 propositions, like 5 statements. And I'm not gonna show the proofs for all of them because that will be very, very tedious. So I'm just gonna make it not as much tedious by showing the proofs for only one of them. Because, the cool one, and that's the one I want to show the proof of. So for the first proposition, I'm just adding a little bit of notation here. So I have my M. My M is the set of all incomplete variables that I have. So let's say I have 3 incomplete variables. So I'm going to have M1, M2, and M3. So I here is just the name of incomplete variables that I have. It's just adding a little bit more notation. And the first proposition here is that if M as a set and S are deseparated, that's what I mean with the subscript G there. If they are if are deseparated conditional on C, then my conditional independence condition holds. And that's just like follows like directly from sort of standard separation rules. So it's not something I need to, that I don't feel like it makes sense for us to discuss too much today. But the point of this proposition is that it allows me to focus my attention on individual incomplete variables one at a time, because then I can just, invoke proposition one and sort of make conclusions for the whole thing. So for the remaining propositions, I'm just, looking at one specific incomplete variable, like say the first one, like the outcome or whatever it's missing in your data set. And now the proposition 2 and 3, I'm not going to show the proofs. I have the proofs at the end of the slides if you really want to have a look at it. But for the main part of the presentation, I'm just going to state what they say. And, I'm a very trustworthy guy, so you can just trust me, and proof by trust. That's a good one. So again, we are looking at one incomplete variable, m sub I. And we have a set of complete variables. We can have, say, 10 complete variables. So we have, C1, C2, C3, all the way up to C10. So just K will be 10 in this example. And I also need to define this bit of notation, Cj star. Cj star is just the set of all covariates excluding a specific covariate. So for example, C1 star would be C2, C3, C4, all the way up to C10. C2 star would be C1, C3, C4, C5, all the way up to C10. Is that clear? So here comes the proposition. Now again, some new notation here. The negation symbol in front of the expression, I'm just saying, so inside parentheses, I'm saying that S and Cj are independent conditional on Cj star. So what I'm saying is that they are not independent. I'm negating the independence statement. So that's just the notation I'm using to express lack of independence. So what the proposition says is that if the selection indicator is not independent on Cj conditional on Cj star, that is, if there is one covariate that is associated with S, conditional on all other covariates, like that's just like a simpler way to put it, then I know based on assumptions A1 to A1, A2, and A3 that I must have at least one of A or B. If that's true, then either I have a path between Cj and S that points into S. The double arrow there just simply means that it could be either pointing into Cj or out of Cj, just a shorthand for that. So I don't need to have like, A, B, C, D. I can just have everything more in a more compact notation. So if this dependence condition is true, then given assumptions N1, A2, and A3, I know that either A or B is true. A is I have an open path between Cj and S that points into S, containing the incomplete variable I'm looking at right now, and that is open conditional on Cj star. And or I have B. B is just saying that I have a path between Mi and Cj, either pointing into Mi or out of Mi, pointing into Cj or out of Cj, that does not contain S and is open conditional on Cj star and S. This is not trivial, like it's not obvious to see why this is true, but the proof is just slightly tedious. So that's why I have it in the slides if you want to have a look at the end. But for now, I'm just stating the proposition because I'm gonna use it later. Yeah.
So one point of clarification, when you read out A, you said containing M, but read not containing. Just want to make sure that I get that right. Does A not contain M or does it contain M?
It does not.
Okay.
Yeah. I said the other way. Oh, sorry, yeah. All right. So I don't expect you at this point, like to, I'm not saying I'm capable of, but I don't expect you at this point to like to understand why this is true. For now, just trust me. So I need now a third. Again, not a trivial one. And again, the proofs are at the end of the slides if we want to go down the route of verifying the proof. And it's a similar proposition, like I have a dependence condition, and I know that this dependence condition given assumptions in A1, A2, and A3 implies that either A and or B is the case. What is the dependence condition? That the missing, the incomplete variable under consideration is associated with selection conditional on complete variables. That's the dependence condition. And what is the implication? The implication is that if that's true, then I will be in at least one of these two situations. A, there is a path between Mi and S pointing into S. The pointing into S part follows like from the sink assumption, from the A3 assumption. And this path does not contain Cj and is open conditional on Cj star. So, and B is actually equal to the B of proposition 2. I have a path between Mi and Cj, not containing S and open conditional on Cj star and S. Again, not trivial, not something that you can sort of, oh yeah, it's intuitive, at least not to me. But again, proofs at the end of the slides if you want to go down the route. The point is, do you get like what the propositions are stating? Okay, that's all I need for the rest of the presentation. So essentially, like in a higher level view, I have a dependence condition that implies that at least one of those things must be the case. And another dependence condition that implies that at least one of those two things must be the case. And those are the two like key results I'm going to use for the main proposition. And this one I am going to show the proof proposition. Yeah, of course. Yeah.
Does this have to hold for every Cj in C or for one Cj in C?
You mean proposition 3?
Yes. So your initial condition is about the sets.
It's going to be for a special Cj that I'm going to show in the next
Cj in C for which one of those two spots?
Sorry.
So your proposition is then there is one Cj.
Yeah, it's one. Yeah. And now this is the key result. This is the key result of this seminar. We start with two empirically verifiable conditions. That's why they have like the E there to like remind us that they are empirically verifiable. E1 and E2. The first empirically verifiable condition is S and Cj are dependent conditional on Cj star. That's the exact same condition of proposition 2. And the second condition E2 here is Mi and Cj are independent conditional on S and Cj star. So those are two empirically verifiable conditions. And the claim here is that if the two conditions are satisfied by at least one of my complete variables, then I am able to infer that the incomplete variable and selection are disseparated conditional on the complete variables. So here, finally, we are arriving at a cool result. But we're starting to get close to our key condition of interest. For now, just with respect to one incomplete variable. So this one I do want to go through the proof. So by proposition 2, what was proposition 2 saying? That if I had exactly this condition here, then I know that at least one of either A or B must be the case. What is A again? There is at least one open path between Cj and S, not containing Mi, and open conditional on all other covariates. And or P, there is an open path between Mi and Cj, not containing S, and open conditional on all other covariates and S. So this is just like a recap of what proposition 2 said. Again, now a recap of what proposition 3 said. If the complete variable I'm looking at and S are dependent conditional on C, then this implies that at least one of those two things, C, an open path between Mi and S, not containing C sub j, and open conditional C sub j star, and or an open path between M sub y and C sub j, not containing S, and open conditional C sub j star and S. So I'm just now restating the two propositions, the result of the two propositions that I did not prove. Prove it to Kate yesterday, but no, yeah, yesterday.
Yeah.
Now I'm going to invoke finally the faithfulness assumption. Proposition 3 talks about, independence. But because I'm assuming faithfulness, I can equate, dependence with the connection. I know that dependence implies the connection, but what I'm saying is that those things are equivalent. Just, it's two-way rather than one way, and that's going to be useful later. So, if I combine steps 2 and 3, essentially I just repeat step 2, replacing the dependence condition with the deconnection condition. And I arrive at step 4. And what we need to notice now is that this implication here, implication that I'm labeling D, is exactly the same as the implication I'm labeling B. Okay? So now let's try to put this together and notice that we can partition our world in the following way. If E1 implies that at least A or B is true, and this deconnection condition implies that at least C or D is true, then if both conditions are true, if both E1 is true and this deconnection condition are true, then I either gonna have A C or A D or B C or B D, right? But B and D are the same. So that means that if both conditions are true, then I am in the situation where both A and C are true, or at least B, which is equal to D, is true. So I have a partition. So if those two conditions are true, I know that I'm either in situation 1 or in situation 2. That must be the case. And what I'm going to do now is to go through case 1 and case 2 and see what happens. Let's consider case 1 first. What was case 1 again? If we are in case 1, then we know that we have a path of the form, a path between Cj and S that does not contain Mi, that is open conditional on Cj star, that was A, and that we have a path of the form A sub y a path that is a path between M sub y and S that does not contain C sub j and is open conditional Cj star. This is just C. So I'm just saying, you know, if I have A and C together, I have any A and C together. That's just what I'm saying here. But notice what happens here. If I have those two paths simultaneously, then that means I have a path between C sub j and Mi that has S as a collider. And I know that this segment here is open conditional Cj star by step 6, and this segment here is open conditional Cj star by step 6. Which means that if I condition on now not only on Cj star but also on S, the path between C sub j and Mi is going to become open, because this is open conditional Cj star, this is open conditional Cj star, and S is a collider. So if that's the case, then we have M sub y and Cj being deconnected, conditional on S and Cj star. This is just expressing in a more compact notation what that means. Okay. So if I am in situation 1, this must be true. That's essentially what I'm saying. Now let's see what happens if we are in situation 2 of the partition. If we are in the situation 2 of the partition, we have case B, which is equal to D. And what was that saying? That was saying that we have a path between M sub y and Cj, not containing S, and open conditional on Cj star and S. That is essentially the same thing back again. So what did we see here? Both cases of the partition are sufficient for the same implication. Both cases of the partition imply that this deconnection condition is true. So the conclusion here is that if we assume E1 and we assume that M sub y and S are dependent conditional on C, which we assumed and got the partition that we explored, plus the 3 assumptions that we have been using all the time, then we know that E2 is false. This is just what we show. But that implies by contraposition that if E1, E2, and A1 to A3 are all true, then this must be true. It's just, proof by contraposition. And this proves the proposition. I know it's something that's a little abstract and like hard to follow when someone is just like talking about it. Something that you really need to like stop and, go through it slowly. I'm just sort of trying to present a rough, an introduction to this notion. But the point of all this is that now, starting from 2 empirically verifiable conditions, we were able to make conclusion about something that's not directly empirically verifiable. And something that is useful for us in terms of trying to deal with selection bias. But this is just for one of my incomplete variables. Perhaps I have 3 or 4 or 5. Well, I can just repeat that for all of them. If all 5 incomplete variables, for example, satisfy the conditions of the proposition 4, then I know that for each one of them, they are disseparated on S conditional on the complete variables, but that just means that M as a whole is independent on S conditional on the complete variables by proposition 1. That's why proposition 1 was there. to allow me to like put everything together at the end. So that's pretty much what this is all about. So as next steps for this, there is like more to explore here, even in the non-parametric setting. For example, I can try to check if I can use some extra assumptions to try to have a method that gives me stronger conclusions, or perhaps, replace some of the assumptions I'm invoking with different ones to try to play with that a little bit. And in terms of like actual practical implementation, there's going to be a whole host of other issues that can come into play here in relation to, model specification, in relation to statistical power, and all sorts of those things. But I didn't get there yet, so I'm not worrying too much about them at the moment. So that's the sort of uninteresting part of my presentation. The interesting part of it is always this. As I always show pictures of my family at the end of my presentations. Those are the pictures from the last time I was here, and those are the more recent pictures. And these are the most special elements to my wife, who takes care of me and our kids. And thanks for everyone for being here, for putting up with me during this rather dry presentation. And please do feel free to ask questions. Thank you.
Thanks very much, Fernando. That was a lot to digest. Open it to questions if there's anyone. I mean, maybe.
Mine's quite simple and probably naive one. I just about followed through because I do trust you. And I was wondering is it possible to say if you went up to 3 covariates and 3 M's, say, or something, do you think it's possible to have like a DAG running alongside to show those sort of concepts of there's this pathway or not pathway, or is it just too, is that something you've tried, or is it just too crazy?
You mean from the perspective of presenting this, or for using this in practice?
Both in terms of kind of understand. I suppose my brain always, I'm quite applied, and so I'm always trying to think of like what variables that would be and what the pathways would be.
Yeah, in terms of the practical use of it, like the whole point is like that you don't have to draw the DAG. Like that's the kind of point of it. Because drawing a DAG in practice is very, very difficult, especially if you want to do it like in a justified way. But I'm not saying don't do it, I'm just saying that
Oh, no, I'm definitely not going to do it. I want you to do it.
No, I'm not going to draw DAGs, like the whole point of it is like, so I don't have to do it. But I do see, like, at the same time, I don't want this to be seen as something that sort of replaces the need for like subject matter input into, because I mean, for example, you're gonna have to select your covariates to condition on here, and I'm giving no guidance whatsoever in how to go about doing that. And this is another piece of research I can present, in the future on how to go about doing it without drawing a full DAG. It's borrowing from the disjunctive cost criterion from Tyler Vandervelde, but yeah, so I think from like a practical perspective, that might be a value, like in adding DAG or representing your prior knowledge in some way to guide you in the covariate selection process. But that's not required like for this to work. From the perspective of presenting it, I think that's probably a good idea. Now that you're saying it, sounds like silly for that I didn't do it. Maybe I should have done it. Yeah.
I mean, if the results have either or conditions attached to them, so you'd have to do a lot of DAGs to.
Yeah. It will be quite a lot of DAG drawing.
I guess from a practical perspective, if you had drawn a DAG, say, to decide which covariates to select, then it would be easy to assess the conditional independence assumptions that you want to test in the DAG.
Yeah, but then if you draw the full DAG like you believe in it in a way, then you know, you will be able to look at this like from the DAG directly. But of course, you can say, oh, here's my sort of best shot with using the DAG, and I'm sort of trying to like sort of triangulate with this. Then you know that's something you probably might want to do. Yeah, yeah.
So I don't know if I understand correctly, so it's more a question about my understanding, I guess. This seems implicitly about variables missing within the data set, not so much there a set of variables where they aren't representative of a larger population, right? But in many cases, you might have summary statistics on the larger population, like distributional, like I know in the general population, how weight is distributed, I know how age is distributed, I know what medications are used.
Yeah.
Does it like readily extend to that situation?
Yeah.
Okay. So C, I guess C doesn't necessarily imply that I have that variable on everyone. It just means like I have meta statistics on C.
Yeah, but like for example, if you want to have to use this for like saying, oh, can I sort of transport the results to this other population? You're gonna need information on C for both the population you're trying to transport to and to the population you're transporting from.
Right.
Because he's gonna be the sort of link between the
the
two. Whether this comes in the format of like individual level data or in the form of like just knowing like the joint distribution of the relevant variables, then you would influence like how you go about like implementing it in practice. But from like a non-parametric perspective, you wouldn't influence things.
I think because I think the important there is you need to know the joint distribution to see. So just having the marginals in your full population isn't enough.
Yeah, I'm assuming you know the joint.
Yeah, no, I'm just thinking because a lot of people try and do it with just the marginals and you can't.
No. So because you need to test their dependencies.
Yeah.
Right.
Yeah.
So you
either need to have it or you need to, because my Caesar skips. Well, surprise. They always are. So if I can make assumptions about their dependent or independent.
Oh yeah.
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 And that's a bit like the test that Tin Yang did for selection in like if your SNPs are associated with a sample, then you've got selection. Like you could if you assume that
they
they're
collide.
Yeah, like SNPs in different chromosomes, for example.
I
mean,
you mean collisions between SNPs on different chromosomes.
Huh?
No, assuming like
Oh,
you can
independent
assume
or
that they are independent, yeah. You've got to assume something.
Yeah, but they really are usually. No.
Yeah, so for example, in this case, my starting point for this presentation is, all full on like non-parametric, but but in a specific application, I think I can come up with a reasonable approximation to the joint distribution that I need by making some assumptions that, you can do it.
What would follow from that is like, would it help at any point? Because you had certain arrows going into feed. That's some.
Yeah.
I think there are situations where you can like empirically verify that all arrows come out of C.
Yeah, like some sort of it would be helpful in some applications. Something I did not say, and perhaps that's a good time to say it, is that those two conditions are sufficient for this to be true, but they're not necessary. And having C's that are exogenous, and by exogenous, I'm just saying to mean what you just said, then you can modify this slightly to make this both sufficient and necessary.
Okay, so that would be really helpful.
Yeah. Those two statements would be modified slightly, but you would be in this rather nice situation. The reason why it's not sufficient is because it could be like colliders and stuff,
Yeah.
where do unmeasured variables fit to this? Like, I think it's still well, so you obviously can't condition on them, but if they're present within their these conditions still hold, and you can still kind of come to the conclusion at the end, right? It's just one of the things that we kind of came across. As soon as you had unmeasured variables within the DAGs that were causing missingness and something else, then quite often that ended up with us being stuck. But I think it's just something you may need to consider, but I think it might still be okay because you're just sort of verifying things from
Yeah.
the dependence.
Yeah, I didn't make any assumptions about absence of unmeasured variables. So that's kind of like the point of this is to in a way, like if you really believe in the assumptions the method requires, then you don't need to worry about unmeasured variables. That's the kind of whole point of it.
Because they can just exist on those paths, but you don't need to like
No.
what they might be.
No,
Doesn't matter.
no.
Does that come in the faithfulness assumption?
Hmm?
That sort of falls in the faithfulness.
Not only on the faithfulness assumption. And I don't think it's the assumption that's mostly relevant to it. What it really comes down to is the fact that, what it comes down to is that for some conditions involving measured variables, I know that they are sufficient for some structures of the deck. They impose some restrictions on the structure of the deck. And it turns out that those restrictions collectively are sufficient for something like this. That's like basically what it boils down to. So, in between where I have like ... I can have, whatever you like. It doesn't really matter. I know it sounds strange, like, it's and again, I don't want this to be seen, oh yeah, just throw all sort of, considerations about prior knowledge, etc., out of the window and start automating. I really don't believe in that. And for the simple reason that, you're still gonna have to select your seed, and I'm giving you any guidance. And, if you start to, let's say, I'm gonna sort of do an iterative process, adding and removing seeds until the conditions of the proposition 4 are satisfied. If you do it, you don't know if you're actually finding a valid covariate set for selection bias adjustment, or if you're optimizing for violations of, say, A2 or something like that. So that's why, you want to have a principled criterion for selecting your covariates. And this is just like an extra, the way I see it, you have like you select your covariates as you normally would, and then you just sort of throw at them yet another layer of challenge, which would be with something like this, rather than use this to select your covariates. I personally wouldn't recommend, as I wouldn't with the confounding thing, I wouldn't recommend that in general.
Okay, any more questions? Maybe online? Does anyone online?
Does when you sort of do it in the non-parametric case, does it mean that you don't have to think about interactions explicitly? Because more generally, does it link with a Plastelis and Gates work, which showed that interaction is like one of the most important aspects of generating?
Yeah, so if I were to do this in practice, which I'm gonna have to at some point, I'm gonna then start to worry about other things like, proper model specification and interaction are gonna play a role there. Statistical power because this relies on, saying that something is not associated. That's gonna critically rely on statistical power. And all those sorts of things are gonna play a role.
Yeah, I mean, I suppose specifically like a lot. Well, I might be getting this wrong, but like you know, you really increase the magnitude of bias quite substantially when you have interaction. And the marginal influence on selection isn't so severe compared to the interaction.
Yeah, I think this doesn't look at that.
It doesn't.
Yeah.
I suppose you could think of it the other way around, as like our work can be a violation of faithfulness, perhaps, like if you have these two variables causing the collider, and it just happens that their model is specifically a logarithm model without interaction, then although they have arrows pointing that they're independent. So
That makes
Yeah. And this kind of thing, it's kind of like forbidden by assumption in a way.
Yeah.
And I'm not sure, like, you know, if we have like you know, if you are conditioning on a collider, but you are in a scenario like what Apostles described, what will happen with this? I'm not sure if you would detect something or you wouldn't detect something. I would hope you wouldn't. But again, my whole I try to not, when I try to like develop methodologies, I try like not to, oh, for it to work, I need for like parameters to cancel out. So I always tend to think more structurally. And yeah, that's why I'm not. But again, when you go to work, the real world, then you can, you should start to think about things like that. And like, say you don't have the interactions, which signal that you don't have a lot of bias. Is that true?
So if you assume that you're in a collider scenario and you assume that your model for the collider is logarithmic and there are no interactions in the model, then you have no bias. But this is quite a specific scenario. It's like, I have the feeling that in practice, the selection process will rarely be truly logarithmic. So it makes much more sense to start with an unparametric setting and then take the special cases separately.
But I guess the point I want to make is that, you know, those are just tools that you have, you know, that you can use as you see fit in your particular application. The reason why I particularly like this, and I know I obviously have conflicts of interest here, is that it relies on like a general sort of parametric theory. Try to make it less boring with, you know, the emojis, but and the pictures of my friend.
Here or online?
Thoughts about sort of, sorry.
No, I was going with you, so.
Okay. Auxiliary variables, like the covariates you have within the models don't necessarily have to be the analysis model.
No.
The weight model could be different, and the imputation model could also be different. I think a lot of this applies to the imputation set as well. And I mean, for our purposes, we'd be really interested in trying to figure out where the auxiliaries fit into it and just making that as clear as possible. That I think applies to both IPW and MIE.
Except in IPW, you know that the auxiliaries have to be complete. Otherwise, you can't use them. Whereas in MI, there's the complication that the auxiliaries themselves can be incomplete.
Yeah.
In which case, you probably just. And then there's whether that you put them in or not.
Yeah. And I mean, again, for something like this, it's hard to incorporate a lot of like nuances that are going to come, you know, in like specific things, because it is supposed to be something general. But I'm not, you know, it might very well be the case that, for example, oh, I'm not able to recover the joint distribution, but I'm able to get, you know, valid estimates of the parameter of interest. But you wouldn't be able to like necessarily be able to figure this out with something like this, because this is like, you know, non-parametric and I cannot accommodate like some aspects of the joint distribution being recoverable and some aspects not being recoverable with something like this. But I do think it's still cool like that, making relatively few assumptions that can recover
Agrees.
sort of cool, useful, potentially useful information.
It's really useful for testing a lot of the way we're thinking about messing at random now. I think once you finish with it, there's going to be a ton of like extensions that are possible to different settings.
Yeah, and I mean, one thing I want to say before we finish is this is kind of in line with how I have been thinking about doing things over the last few months. We discussed about this briefly this morning. Strictly speaking, the scenarios where we are able to satisfy the conditions of proposition 4, that's going to imply, I didn't go in detail here, but that is going to imply that C is like larger than it needed to be. That is going to imply that like essentially because conditional non-additive covariates, the C is not related to the missing variable. Like that's essentially why that's the case. So, you know, it is possible that your C is minimal, for example. In that case, you wouldn't be able to detect that it is sufficient. But, you know, trying to detect the bare minimum is very difficult. And I have been sort of leaning more towards sets of assumptions that are rich enough to give me empirical grounding. And I think this is one of the examples where that illustrates this sort of way of approaching things. Otherwise, we rely on assumptions on things that are so thin that can be explained by like a zillion different things, and you can never falsify things or confirm things. So I'm like comfortable in making in only being able to detect a C that is valid when it is more than enough, because this will be a situation that is prone to be you know, to be detected, at least with a methodology like this. I'm not saying that with other means you wouldn't be able to do better than this, but that's kind of my sort of epistemological justification for being interested in assumptions that are strictly speaking stronger than. It's kind of like, you know, when I presented my seminar last week, for those who were here, when they talk about like various tests for the inside assumption, it was like detecting something that's like technically stronger that you need for MREGR to work, but you know, it's good enough, I suppose. Yeah, I hope this was not too boring for everyone.
I think data's difficult.
It's annoying.
No, it's not.
Right.
Maybe this can be interesting.
Well, for us, for like methodologists, it's interesting. For empirical researchers, it's annoying.
On that note, we're about at the 1 hour mark. So thanks very much,
Yeah.
Fernando. That was
Thanks.
great.